Hello again, method students. In this video, we're going to look at 16E, the last exercise of chapter 16. And this involves using the normal distribution to approximate a binomial distribution. And so if you think back to what binomial distributions are, they're identical repeated trials where there are only two possible outcomes. If you have a binomial distribution with a really large number of trials, so where n is a pretty big number, it's actually possible to use a normal approximation for the binomial distribution. Now, you only ever do this if it's really clear that that's what the question's instructing you to do. And the way this works is you first calculate the mean and standard deviation of the binomial distribution, and then you apply the calculations associated with normal distributions. Let's have a look through an example how this works. So we've got Andre and Pete who regularly play tennis against each other. And each time they play, the probability of Pete winning is 0.6. Over the next year, they're going to play each other 50 times. Okay, let X represent the number of times that Pete wins. So this is a binomial distribution question to begin with, because we've got these repeated trials and the fixed probability of success. And so the mean, remember that for the mean, which we also can write as the expected value of X, so expected value of X, which is also written as the mean, for a binomial distribution is just n times p. And so for this question, we've got n equals 50 and p equals 0.6. That's the probability of success. So it's 0.6 times 50, right, which equals 30. So the mean is 30. In other words, we're expecting Pete to win 30 games out of 50. The standard deviation of X, well, remember that we first find the variance of X, which is sigma squared, and that's equal to NP times 1 minus P for a binomial distribution. And so this is 0.6 times 50 times 1 minus 0.6. So that's going to be 30 times 0.4, which is actually 12. And I've just barely left myself enough space to write this here, but remember that the variance, the standard deviation, which is what we're trying to find, is the square root of the variance. So the standard deviation of X, which is equal to sigma, we write it as sigma, is the square root of 12, which if we were to simplify that, we could write that as 2 root 3. And so we get, I should write that a little bit more neatly, we get, I'll put it here, mean equals 30, standard deviation equals 2 root 3. Alrighty. Part B, it says use the normal approximation. So this is where you only ever use this method if it explicitly says to use the normal approximation. Otherwise, you're never going to use this. To find the probability that Pete wins more than half of their matches in the next year. Okay, so what we're trying to work out is the probability that X is greater than 25, because half of their matches would be half of 50. So the probability that he wins more than half their matches would be the probability that X is greater than 25. Now, if we're going to use the normal approximation, we're going to go to our calculator and we're going to use norm CDF. So we're going to, on the CAS, use norm CDF. And so we're going to treat this, even though it's technically not, we're going to treat this like it is a normally distributed variable. And so we're going to go interactive distribution continuous, norm CDF, and we're going to say that the lower value is 25, the upper value is 50, the standard deviation is the square root of 12, or that 2 root 3 that we found before. I'm just going to put it in as the square root of 12. And the mean is 30. again, which is what we calculated before in part A. And so this is saying the probability, if we use this normal approximation, the probability that Pete will win more than half his games is 0.9255. And so using this normal approximation, we get a probability of 0.9255. Let's go to 4 decimal places. Okay, so that's really the idea of this exercise, that you can use the normal approximation to find a probability of a binomially distributed variable. Now, in part C, we're going to repeat this, but it says to use the binomial distribution. So this is like the way that we would normally do this, to find the probability that Pete wins more than half his matches in the next year. So if we were treating this as a binomial distribution, which is really what it is, then we would say the probability that X is greater than 25. Remember that with binomials, we actually can't have, we can only have whole number results, right? So he can only win 25 games or 26 games. He can't win like 25.2 games. So really this is the same as saying it's the probability that he wins 26 or more games. And if we think of n equaling 50 and p equaling 0.6, then what we can do is on the CAS, we're going to use binom CDF this time to get our probability. And so it's interactive distribution discrete, binomial CDF. We want him to win 26 or more. So it's 26 to 50 is the range of successes. The number of trials is 50, and the probability of success on each trial is 0.6. When we hit OK, you can see that we don't get the same probability as when we use the normal approximation, but it's relatively close, right? And that's the whole idea, that it's a normal approximation. So we're approximating the probability using a normal distribution, but the binomial CDF value here has actually given us what the answer should be, if you like. Okay, so again, to 4 decimal places, that would be 0.90. 219, so it's actually 2.9022. All right, so when we compare that to what we got in part B, you can see it's not the same number. Now there's a couple of things going on here. We weren't expecting the exact same number because this is an approximation, whereas what we've done in part C is a more precise calculation. But the other problem that arises here is that when we are treating a variable as if it's normally distributed, we're treating it like it's continuous. Okay, so when we say the probability that X is greater than 25, that's really treating it like X could be 25.1 or 25.2 or 25.67 or something like that. Whereas when we use binomial calculations, we treat it as a discrete variable. And so therefore, when we say X is greater than 25, we really mean 26 or more. So this might have been a more accurate approximation if we had, when we use the normal distribution, if we treated it as X is greater than 25.5 or X is greater than 26 or something like that. It's not really what you're supposed to do. So there's a couple of reasons why the approximation isn't super close to the correct answer. Another thing that's worth noting is that the larger the sample size, so if these guys played like 500 times or 5,000 times, this approximation would get closer to the correct answer. So I guess in summary here, only ever use the normal approximation if you're explicitly told to, like we were in part B. But in every other case, if it's a binomial question, you'll use the method that we used in part C to actually get the answer, because this is the more precise answer. All right, so that's using the normal approximation to binomial distributions. It doesn't come up all that much, and when it does come up, it's going to be really explicit. So good luck with exercise 16E. As always, let your teacher know if you need help with any of the questions. Otherwise, see you in the next video. Cheers.